Good afternoon, and thank you so much for the kind invitation to speak today. My name is David Mohaisin, and I'm a professor at the University of Central Florida, where I lead research in system security, privacy, and applied machine learning. In this talk, I'll be sharing some of our recent work at the intersection of AI and security, and looking at both the opportunities that AI provides in enhancing defenses and the new risks it introduces when misused. I'm very grateful for the opportunity to present this work here, so thank you so much, Marinos. And I look forward to an engaging discussion with you. So let me start with a little bit of a historical background about how we got here with AI. So in 2006, Geoffrey Hinton's deep belief network reignited the interest in deep learning. And by the year 2009, the ImageNet dataset has been introduced, creating the benchmark that would fuel the modern AI revolution. In 2012, AlexNet, also by Hinton and his group, won the ImageNet competition, reducing error rates and showcasing the power of GPUs for training. And then in 2013, Wörtervik transformed neural language processing by capturing semantics meanings in vector space. Just a year later, in 2014, generative adversarial networks, or GANs, opened the door for synthetic media generation. And in 2015, ResNet introduced very deep neural networks with skip connections, further pushing models' performance. Moving forward, in 2016, AlphaGo defeated Lee Sedol, a historic milestone showing AI's ability to master complex strategy games. And in 2017, transformer architectures emerged, revolutionizing both NLP and deep learning as a whole. And in 2018, Google introduced BERT, which is quite a revolution back then, enabling what we see of powerful bidirectional understanding of languages. In 2020, GPT-3 was introduced and demonstrated large-scale language generation, setting a new benchmark in natural language processing. In 2021, AlphaFold 2 solved the decade-long challenge of protein structure prediction. In 2022, ChatGPT brought generative AI into the mainstream, while diffusion models transformed image generation. And finally, in 2023, we saw the release of GPT-4 alongside major contenders like Claude, Palm, and Llama, marking the era of competitive large-scale foundational models. In 2025, early we had GPT-5, which is an improvement over GPT-4 and all of its predecessors. And now we are seeing the advances in AI alignment, safety research, and specialized agents. Multimodal AI expands into vision, robotics, and many other applications that embody intelligence. So AI is everywhere. And let's look at software development where AI is being heavily used or being hyped by some industry individuals. So this is a news story from a couple of days ago where it says that 9 in 10 software executives want custom AI agents in their firms. Another story from Goldman Sachs saying that AI agents would boost productivity and size of software market. Another story, Microsoft saying that AI is finally having a meaningful impact to developers' productivity, and 80% of people will be disappointed if they do not use it. And another story about IBM and IBM Watson X that says that its capabilities for code assistance would impact AI-powered software development. Another story saying that there are 7 ways that Gen AI can help improve software development, and you would be disappointed if you miss on that. Another one from Gartner, a large firm in the US, saying that how AI agents will disrupt software engineering. So clearly AI fuels productivity, but it's not only productivity for the good people, it's also for the villains. And so similar news stories, like for example, this story is a couple of days ago from Wired, saying that the era of AI-generated ransomware has arrived. Another story saying that first known AI-powered ransomware uncovered by ESD research from ESD Research. Another one saying that hackers use AI to automate some cyber crimes, their Anthropic report. Another story saying that Iranian ships have been hacked, and the verified Android developers stating that AI is used for that tech. Another story from Cisco Telus saying that cyber criminals have been using large language models for conducting their cyber crimes. Another story from Anthropic saying that hackers weaponize Claude AI to launch cyber attacks, extortions, and job frauds. Another one saying that from the same entity saying that Claude AI has been used to attack different institutions and getting Bitcoin ransom in the range of $75K to $500K. So clearly AI is being used for good, but at the same time it's being used for bad, creating this arm race. And so in this talk, I will be basically focusing on this arm race. And so why would we use AI for good, particularly in security? Well, security faces several challenges. The data is complex and varied, from code and vulnerability patterns to sensor traces and scans. And the signals are often subtle, introducing indirect kind of clues, making attribution and privacy breaches detections very difficult. Moreover, human analysis does not scale well. So since manual triaging and patching are slow and error prone, and the input themselves are frequently incomplete or noisy, such as partial code or ambiguous logs, this makes it even more difficult. So AI and machine learning in general are well suited for security because they excel at pattern extrapolation, learning from small differences to make powerful inferences. They provide automation and augmentation, enabling scalable solutions for tasks like authorship detection and code repair. Moreover, they offer strong generalization capabilities, making predictions that transfer across domains, languages, and platforms. And through representation learning, embedding can also uncover hidden structures in complex data, such as signals from wearable devices. So we start with data from a large number of sources with the hope that representation through embeddings, encodings, large language models used for intelligent crafting of modalities to address some security problems in different applications through attribution, vulnerability detection and contextualization, code repair, and privacy breaches understanding. And so in this talk, this is going to be the focus. This talk is going to explore the AI-driven arms race in security through these applications. The first of those applications is going to be code authorship attribution. And so code authorship attribution asks a very fundamental question. Given a piece of code, which author has authored this code? And in light of the recent advances in generative AI, given a generated code, I want to tell whether this code is generated by a human or a machine. And why I care is for multiple reasons. So for intellectual property and legal rights, I want to establish ownership, licensing, attribution, and giving the proper credit for the code being generated. For understanding collaborative and accountability aspects, I want to track blame or credit in codes where vulnerabilities may arise, and ensure maintainers can communicate effectively about their code changes. For understanding and maintainability, knowing the original author provides context and help kind of retain knowledge critical to sustaining code bases. And for security and trust, where provenance and auditing are essential, authorship plays a role in protecting malicious code, tracking malware origins, and ensuring compliance. So in short, what I want to do is that I want to understand those capabilities in context. And so this problem is not really new. So by the time we started working on it in 2018, there was a plethora of efforts in this space. And those follow a different kind of directions. So given a set of program code samples, the goal is to determine whether we can accurately attribute them to their authors by analyzing coding style, elements like indentation, naming, space, and comments, and by using some statistical models to capture each author's unique fingerprints. And so this has been done in other works. Even some improvements have been done beyond surface syntax. Attribution also considers logical patterns, designing choice, API usage, data and control flow graphs, semantic embeddings, and function signatures, while commit history, authorship logs, and timestamps provide some additional context. And the main challenge here, however, is scalability. So when the number of authors grows large and become difficult to handle with those manual annotations and manual extraction of features, it becomes very difficult to manage. Moreover, there is a great language dependence where one scheme that is run for a given language will not be generalizable to another language or transferred to another language, which limits generalization across programming languages, across data sets with different sizes. So our thought for addressing this problem is, well, if advances in AI can be used for kind of addressing automation problems, we can then use learning-based approaches, training a neural network to directly predict authors based on the raw contents of programs. And this removes the need for handcrafted features and allow us to learn representations automatically. And the key idea moving forward is that since instead of manually designing features, we would want to let neural networks learn those features or patterns directly from code to predict authorship labels. So this is exactly what we do. Code authorship attribution is done by training a neural network to predict the labels or authors based on the program contents. And so how do we handle the program contents? So this diagram here shows the deep learning pipeline for code authorship attribution. We start with the code files, which are then converted into TF-IDF representations. These representations are very cheap to kind of produce and capture term frequency and importance across the code corpus. Next, the data flows into a stack of 3 recurrent neural network layers using LSTM and GRU to capture sequential patterns and stylistic dependencies across the code. And then these hidden states are passed through 3 fully connected layers, which refine the learned pattern representation into dense vectors suitable for classification. And finally, classification is performed using a random forest classifier with 300 trees, which outputs the predicted author label for each code instance. And this kind of hybrid approach, combining the sequential modeling power for deep neural networks with the robust decision boundaries of random forest, can be used for improving the accuracy of attribution. So how does it perform? So here are some results. Here we see the performance of deep authorship attribution across different programming languages. For the Python programming language, accuracy is extremely high. So we have over 99% on both single-authored and multi-authored code. Even with obfuscation, the model remains robust, dropping only slightly. For the Java programming language, the results are similarly strong, with accuracies above 99% and resilience against obfuscation attacks holding above 96%, while adversarial manipulations reduce success rates to only about 1.5%. For C++ attribution, it remains also highly accurate, around 99%, but obfuscation has a stronger effect, lowering the attribution by roughly 4%. Extensions of this work have been also done, demonstrating various strong advances. So again, this work started in 2018, and the last published work is just in Press, published in 2025. So this is a work that we have been working on for a long period of time. And so in recent work, we had attribution that can be done line by line for multiple author codes. This is a work in BITS 2020. In another work, we have identified that identification can still be robust even under obfuscation. And this is a work that we have shown earlier in an extension in 2021. And finally, in 2025, we have shown that you can still implement defenses further, strengthening resilience, as shown in our forthcoming Shield framework. And the idea of Shield framework is that you can kind of obfuscate the way that you write the code by creating a large number of templates to follow, so that you can conduct something similar to flattening of the code. So overall, code authorship attribution is highly effective with only some modest degradation under adversarial conditions, highlighting both its promise and the arm race dynamics in secure authorship analysis, particularly given the defenses that we can implement for swaying the kind of identification itself. So now that we have covered the general code attribution, let's shift our focus on the AI-generated code. And so, as we have seen in the news stories that I introduced earlier, AI is now heavily used across domains, from assisting developers to automating tasks to more concerning applications like malware authorship or even academic plagiarism. So this raises an important question. When we see a piece of code, can we tell if it is written by a human or by an AI? And the answer matters for both audit and trust. In the security domain, it can help attribute malicious codes back to the AI systems rather than humans. In software engineering, it is critical for compliance and accountability, for example, determining faults or blames in the case of bugs. So understanding the origin of code, human or AI, will be central to maintaining the accountability, trust, and security in the AI era. So, okay, attribution of ChatGPT generated code, we show that it is feasible. And so we start with the idea that ChatGPT is a reality right now. It was launched by OpenAI, and chatbots built on a large language model. ChatGPT demonstrated a human-level kind of writing skills in both natural languages and programming languages. However, it has been used for all sorts of bad things, can be used for generating malware, can be used for cheating and plagiarism, and can be also be used for generating code that is not really secure. So it has a lot of vulnerabilities. And so for addressing the human languages utterances, 0GPT was introduced and kind of solved the problem more or less with some caveats. For code authorship, that is still if a code is generated by a human or a bot, there is not much work. I mean, since we have developed this work, there has been another traction in academic world for this problem, but back then there is no academic work. And so the idea that we kind of contemplate is, can we use code authorship attribution type of mechanisms to simply address this problem, starting with the source code, getting some statistic features, and then random forest trees, or maybe using the same kind of deep neural network-based kind of model that we had earlier, and then to predict the labels. Can we do that? And well, the answer is that this naive approach for solving the problem produces an accuracy of 8.3%, 29.2% kind of accuracy. So in a nutshell, this kind of approach, although very intriguing, is not really working. So again, the idea here is to find out if attributing ChatGPT generated codes is feasible. And we do that through something that we call feature-based kind of approach, or proxy-based kind of approach, by looking at the diversity of the stylistic features of the ChatGPT generated codes. So to conduct this experiment, challenge statements from Google Code Jam competition are utilized to generate ChatGPT codes. And ChatGPT is asked to generate source codes with challenge statements and their corresponding limitations, input, output, etc. And this is going to be the basically template prompt that we use for generating codes. From 2 different years of the competition, 2017 and 2018, a total of 4,000 codes and 1,600 codes are generated, collected for the experiment. And these codes are used for the naive approach that we had earlier. And the idea here is to look into the diversity of the codes, and if we can maybe sacrifice some of the accuracy for basically less confusion with the author-based codes, so that we can, in a way, attribute to ChatGPT codes. So for that, we propose what we call a feature-based approach, in which we extract the stylistic features of ChatGPT codes using the non-ChatGPT authorship model. That is a model that we built on non-ChatGPT codes, so that we want to basically map the ChatGPT codes to a few authors in the real author codes. And so we group ChatGPT codes based on their features and combine them with non-ChatGPT codes to train another model, a new authorship model. And by grouping the ChatGPT codes based on their features and training an authorship model, the model could learn the common features of the codes and classify them correctly to non-ChatGPT or ChatGPT. From this experiment, we observed a couple of things. First, ChatGPT can generate source codes in various styles, up to 43 styles, which is a bad thing. But second, which is a good thing, although ChatGPT produces multiple styles, it uses a very limited range of styles frequently. And so, and third, which is kind of the results, our feature-based approach is able to successfully attribute ChatGPT codes with an accuracy ranging from 81% to 94% of attribution accuracy, while the naive approach is only hitting the 8.3% to 29.2%. And that kind of accuracy of attribution is at a very small kind of misclassification of the true human authors. Okay, so from this experiment, what we have found is that ChatGPT programming ability is great. It can generate source codes with various styles, and this observation of multiple styles kind of give us the kind of cue in the arm race is, can ChatGPT be used for code stylistic transformation? And so if it is able to do that, then maybe it can sway our detection. So code stylistic transformations are done in involve modifying 3 features in a source code. They are going to be the lexical features, which is the choice of variables and functions names. For example, an author may choose the name of their functions and variables based on their functionality or based on some arbitrary kind of structure for shorter forms. Another one is the layout feature, so indentation, comment formation, and the use of brackets. For instance, one author may prefer a single line comment for spaces of indentation and open brackets on the same line. On the other hand, another author may prefer to use multiple line comments, 2 spaces of indentation, and open brackets on a separate line. The last one is syntactic features. For example, the coding style adopted by programmers can be distinguished by their usage of syntax and control flow, which can be examined through the fundamental data structures of compiler design, known as abstract syntax trees, or ASTs. And so to examine the ChatGPT code transformation ability, and we observed that up to 12 different styles for this particular data set from the ChatGPT transformed codes transformed from a single code style. As a result, this answers our first question. ChatGPT can be used for code transformation. So it is possible. However, this leads us to another question. Can ChatGPT evade our ChatGPT-based transformation, based authorship attribution approach? And so before we are able to answer this question, we conduct an experiment for ChatGPT transformed code authorship with a feature-based approach. So to conduct code transformation with ChatGPT, we utilized ChatGPT code and non-ChatGPT code with two different settings. One is the non-chaining, and the other is the chaining one. And so for ChatGPT codes, we asked ChatGPT to generate a source code based on the Google Code Jam challenge statements. And for non-ChatGPT codes, we utilized one Google Code Jam participant code. And in the non-chaining approach, we asked ChatGPT to transform one source code multiple times, for example, 50 times. And in the the chaining approach, we asked ChatGPT to transform a source code. Then we transform the transformed code of the source code multiple times, and as a result, ChatGPT transforms different code every time. With the non-chaining approach, we observed that ChatGPT code is transformed into 7 different styles, with the non-ChatGPT code having up to 12 different styles. And with the chaining approach, we observed that ChatGPT code is transformed to only 3 styles, while non-ChatGPT code has up to 6 styles. Based on these findings, we noticed that first, ChatGPT could generate more various styles with non-changing approach, and the non-ChatGPT code tends to have more various styles after transformation. So after that, we analyzed the diversity of the styles, and you have multiple styles, but do not know how many of those styles are used heavily. And so from this analysis, we observed that one style or label appears more than other styles, as we can see here in this figure. And so author 48 of the real authors that maps to that kind of have the same style as a majority of the codes that are generated by ChatGPT had about 1,234 times appearance of style out of the 1,600 codes, and this represents 77% of all the codes generated. This indicates that ChatGPT is able to transform source codes, styles, patterns, but it uses a few styles very frequently. And this is very similar circumstance with what we observed from ChatGPT authorship experiments. Therefore, we applied our feature-based approach by utilizing the style that is author 48, and we achieved 100% of ChatGPT classification accuracy while maintaining 90% of authors and 100% of author 48 classification accuracy. All right, so this is it for authorship attribution. So clearly, AI has a very nice application in this arm race. And now we should gear a little bit to another problem, which is vulnerability description enhancement with natural language processing, with AI. So one of the biggest challenges in vulnerability management is the quality of vulnerability description. And those vulnerabilities are often, or descriptions are often incomplete, inconsistent, and ambiguous. And because they are written by natural language, the quality varies widely, and they are difficult to automate or match with specific regions of codes. The poor description has various consequences and implications. So they show that they can slow down patch development, cause missed or inaccurate detection of affected components, and reduce situational awareness for security teams. And this is where NLP can help. So natural language processing enables automated information extraction, identifying functions, components, and causes, and it supports semantic normalization of CVE's data, and can even link descriptions directly to codes, commits, and documentations. All right, so this is it for authorship attribution. So clearly, AI has a very nice application in this arm race. And now we should gear a little bit to another problem, which is vulnerability description enhancement with natural language processing, with AI. So for those who do not really research vulnerabilities, let's step back a little bit and ask the question, what is a vulnerability? So a vulnerability is a weakness in software, and it could be like a buffer overflow, SQL injection, directory traversal, or a broken authentication link. And any flow that attackers can exploit to kind of launch an attack. So the scale of the problem is very massive. In the year 2013, which is around the time that I finished my PhD, just over 1,200 vulnerabilities were reported, and by the year 2022, about 9 years later, the number of vulnerabilities have surged to past 25,000 in a single year. Today, vulnerabilities are discovered daily, and the systems exposed are in the billions, with the IoT devices and the kind of weak software development lifecycle they have. MVD, or the National Vulnerability Database, which is something in the US, is central repo for documenting these issues, but it comes with several challenges and weaknesses. So many descriptions are brief, making it very hard to understand the impact of vulnerabilities. Others are inconsistent, making automation and large-scale analysis very difficult. The result is that vulnerability descriptions, while essential, are oftentimes not rich enough for parameterization, detection, or batching without additional processing. And this is exactly where natural language processing can play a transformative role. And we address the briefness aspect with ZAD, with the inconsistency is addressed with Mujas, two of our systems that we developed over the last few years. And in the interest of time, I'm going to talk only about the inconsistencies in ZAD. So to improve the vulnerability description, we start by considering different kinds of features. These include the original features found in the MVD description itself, auxiliary external features like linked references, and supporting text. And additionally, we have additional features that can be derived through enrichment and augmentation. But this process comes with some challenges. So first, augmentation. We need to carefully expand descriptions without introducing noise. Second, text encoding. So representations must capture semantics accurately across diverse vulnerability reports. And third, evaluation. So assessing the quality of the enriched descriptions requires consistent benchmarking. At the bottom of this diagram, we have here the data collection and augmentation pipeline starting from the MVD. We extract vulnerability descriptions and their hyperlinks, that is referrals to other sources. And we then process each URL, scrape the contents, and embed the descriptions and link text into a vector representation using some similarity measures. We measure the relatedness and decide whether to augment or discard the information that we have. And finally, the corrected data sets and enriched summaries are produced, which can be used to train a model and improve the downstream security task. This pipeline ensures that vulnerabilities descriptions become richer, more consistent, and more useful information, parameterization, and remediation. So very quickly on the results, here is evaluation of the vulnerability description enrichment. On the left-hand side, we have the performance using different text encoders. The universal sentence encoder consistently outperforms the MPNet, reaching an F1 score of about 0.59 to 0.61, with a precision as high as 0.62. On the right side, we evaluate the generation quality with BART. Human judgments show moderate fluency of 2.69 out of 3, but lower scores for completeness of 2.15 and correctness of 2.16, with overall understanding rated at 2.58, which is quite good. This highlights some of the challenges in producing both fluent and accurate enrichment descriptions, but still reasonable. And at the bottom, we compare training on ground truth versus raw descriptions. As expected, models trained on the ground truth summaries perform better, achieving a recall of 0.61 and an F1 score of 0.55, compared to weaker results when relying on unprocessed descriptions. Taken together, these results confirm that enrichment of descriptions improve both machine performance and human usability, but there is still some room for improvement in generating complete and correct outputs. So moving forward, another application that we look into in this arm race is code repair. And code repair is about automatically identifying and fixing bugs in the source code. It boosts developers' productivity by reducing manual debugging, and supports education by helping learners correct mistakes, enhances software reliability by preventing crashes and vulnerabilities, and speed up development life cycle or cycles by enabling rapid iterations into the CI/CD pipelines. So here we highlight three different ways AI can be integrated into software development lifecycle. First is the code generation flow. A human developer works together with an AI coder to produce code, which is then reviewed and refined by the developer before being added to the code base. Second is the code analysis flow. An existing code base is fed into AI codes, and the coders analyze it for potential issues. The AI then kind of provide insights back to the developer, supporting debugging, auditing, and improvements before changes are committed. And finally, in the fuzzing flow, AI coders generate test inputs for the existing code base. These inputs then help uncover vulnerabilities or unexpected behaviors, and the results are monitored and interpreted by human developers, creating a cycle of continuous test and feedback. Together, these flows illustrate how AI is not only assisting with code creation, but also can be used for analysis and security testing, augmenting human developers across multiple stages of the software pipeline. Or that is the premise. So, in order to be able to test this premise, we need to understand the benchmark of vulnerability detection in AI-based code assistance. And so this workflow shows how large models can assist in repairing vulnerabilities code. So it starts with vulnerability detection, where the LLM scans the code and flags potential issues. If the code is vulnerable, the model proceeds to type identification, classifying the nature of the vulnerability, such as buffer overflow, SQL injection, and authorization bypass. And once the type is shown, the LLM performs function localization, pinpointing the specific function or code region where the vulnerability resides. And the next step is the repair suggestion, where the LLM generates candidate fixes or patches. And these are then passed to the developer for review and verification. And after validation, the secure and batch code is reintegrated into the code base. In this way, LLMs not only automate the vulnerability detection, but also guide the full process of localization, repair, reinforcement of code security, with the humans still in the loop for trust assurance. So to truly understand and benchmark LLMs for code repair, which is our work, we need to look at 4 dimensions. First, a critical evaluation assessing the real potential of LLMs to transform security tasks and separate hype from measurable capabilities. And second, the influential factors, identifying what drives success, whether it is the quality of training data, the choice of architectures, or the integration with the human oversight. Third is the optimal conditions, pinpointing when and where LLMs work best. For example, are they more effective on small localized bug fixes, or do they scale to complex multiple functions vulnerabilities? And finally, limitations, acknowledging the constraints that hold LLMs back from hallucination and incomplete fixes to scalability and explainability issues, so that those 4 pillars would give us a structured way to benchmark, compare, and improve LLMs for secure code repair. And this has been the focus of my group in this space. All right, so a final thing that I want to talk about is, okay, so LLMs can be used or machine learning, AI in general, can be used for good, but they can be also used for bad. And so I will talk about 2 things that are in the bad space. Those are the inference attacks. So, some of the technologies that are being introduced to us, they are introduced with the premise of privacy. So the question that we ask, is privacy real or just a trick of new technologies? And so we test this kind of a question with elevation maps that can betray your runs, and headsets that can spill your secrets. And so let's start with the first one, which is about measuring location from elevation profiles. So many wearable today are equipped with GPS capabilities to track activities, including exercise. The collected data is then visualized and presented back to the users for engagement, and often showing both the raw location trajectory as a map and the elevation profile. And so the uncontrolled sharing of the elevation or data actually of this geodata introduces significant risks. In one of the case studies that we conducted, we observed that adult users often start in their exercise and end them at home and frequently travel to work or school. So location that can reveal private attributes. Exposing these can lead to threats such as stalking and theft. So to mitigate these risks, service providers allow users to hide activities maps, restricting sharing the elevation profiles, and instead of the precise locations, they might allow the sharing of the elevation. So, but the question is sharing only the elevation data truly sufficient to preserving the privacy? And so we answered this question, and we found. And so let's start with the first one, which is about measuring location from elevation profiles. So many wearable today are equipped with GPS capabilities to track activities, including exercise. The collected data is then visualized and presented. So to tackle this problem, we begin by formalizing a bunch of adversaries based on their knowledge and goal. And so these adversaries can range from history of the target, is the capability that we know, to finding the location of the target, city of the target, finding the city of the borough of the target, and then having no information and trying to find the city of the target. And so we build a pipeline. So the pipeline starts with data collection. We compile the three data sets: a user-specific data set, a city-level data set, and a borough-level data set. And the user-specific data set was kind of gathered from a defined group of participants, while the city and borough-level data sets were obtained from Google Maps and open source maps. And then we start with we proceed with the pre-processing, where we design two representation approaches: an image-like representation using heat coding, and a text-like representation using word discretization. And we also develop algorithms to automate parameter selection based on the generated training loss, along with the balanced fine-tuning strategies. Next, we have feature extraction. And for feature extraction, we convert data into discrete feature vectors using standard images and text modalities such as TF-IDF, engrams, and convolutional features. And then for classification, we build a fine-tuned 2D CNN alongside several off-the-shelf learning techniques, as is illustrated here. And finally, for the threat model 1, using text-based features, we achieved a prediction accuracy of 98.5%. For TM2, we also used text features, and the accuracy reached 80%, while for TM3, we had 55% accuracy, highlighting the different kind of trade-offs between what you try to achieve and what kind of information that you have. So to tackle this problem, we begin by formalizing a bunch of adversaries based on their knowledge and goal. And so these adversaries can range from. All right, so that is one. Let's move to the second kind of work that we have, and that is about breaching privacy in AR air tabbing keyboards. So after decades of research and development, augmented reality has finally reached consumers with multiple offerings of AR head-mounted displays, or HMDs. These devices can now come with powerful features that enable diverse use cases, including simulation, training, entertainment, and real-time assistance. To support that, AR technologies introduce new models of interactions. And so those models of interactions can include voice commands, human gestures, and gaze tracking. And one of those is using hand tracking technologies. You can kind of project some virtual keyboard in the virtual environment and use that for typing in. So hand tracking technologies can be used for input. And one of the premises of that hand tracking technology is that this is more private than just having a keyboard, physical keyboard, where users can surf over your shoulder. And the question that we ask, this is the premise. The premise is that this is more private, but the question that we ask are air tabbing kind of keyboards. All right, so that is one. Let's move to the second kind of work that we have, and that is about breaching privacy in AR. So how do we do that? We start again with formalizing threat models. We have three different threat models, including planting a hand tracker near the user and recording hand movement, sitting next to the user with an HMD on by the adversary, or infecting the user's HMD with remotely and kind of obtaining the hand movement. Images are shown here, and imagine the technology being used in a coffee shop where implanting this kind of adversary is not going to be difficult. And so our pipeline for launching this attack starts in 5 stages. We have the first deep key localization, and followed by key tab localization refinement, where we refine the localized based on some heuristics. And then we have the candidate key center generation based on the fact that tips of the finger are going to be in certain location in a space, and those are going to be the highly likely parts of the keyboard. Then we get candidate keyboard reconstruction based on the different instances of observation, and we order those candidates best to worst, and then based on some through should, we kind of make a hypothesis about. So how do we do that? We start again with formalizing threat models. We have 3 different threat models, including a planting a hand tracker near the user and record. So to wrap up, I would like to leave you with a parting thought. AI is not a silver bullet for all security challenges, but it introduces powerful efficiencies that reshape the attack defense landscape. And as capabilities grow, AI will increasingly serve both adversaries and defenders, amplifying the stakes in this ongoing arms race.